and this is the Fire Hose Rodeo.
As we make this transition from fluid statics, of course, so it's a big day for us today. We're making this transition from talking about fluid pressures at a point, fluid pressures on structures due to static fluids, to being something that deals now with moving fluids. So we're still talking about fluid mechanics, but instead of fluid statics, we're talking about fluid dynamics. And these are just a couple of examples of, I suppose, in some respects, machines which work this way. This is the jet lev, I guess, or some such name. The idea is that you can zip around. You can see it's a capsule behind this guy that has a motor in it, a pump, basically a pump and a self-contained power unit. And it supplies this big honking hose, which goes down his back and then is directed in any way he sees fit to be able to move around. Quite an interesting invention. I'm not sure how much it costs. I think it says on one of these in the narrative, which we have turned off. But yeah, interesting idea in terms of being able to get around. I don't know if anyone's ever bought one of these, but I think they're publicly available. Seems like a fun little toy, maybe for 10 minutes, and then you might get bored with it, I guess. But you can imagine it'd be quite useful to zoom around the bayous in the Everglades or something. I guess it looks like that's where it is in Florida. So the Jet Lev Flyer, so-called. And so you can find that online yourself. Yeah, I had this because a year ago this was going on. And so I think it's interesting because just to think how much designs of sailboats have changed. It used to be that the America's Cup was a yacht. I guess it's 12 meters. 12 meters is some kind of formula where you add some different things, width and beam and length and waterline length and sail area and divide by something. And the formula comes out to be 12 meters. And it used to be a yacht, single-hulled yacht. But now, I guess, this was the nail-biting challenge last year where it was, I think, well, New Zealand and the USA. I think New Zealand, it's done in the Bay Area. See the Golden Gate Bridge in the back. It's done over a number of...
They're not used to talking to anybody.
Shut this off. It's done over a number of weeks.
Be enjoying it working together.
And it's, maybe it's the best of 13 legs or something. And I seem to remember it was like 6-0 to New Zealand at one stage, and then the US came back to win it. But amazing boats now that are, they don't bear much resemblance, it seems to me, to the yachts of old. They're all, in this case, these are catamarans, obviously, and I think they go 50, 60, 70 miles an hour. They go fast. And so it's kind of an interesting marriage between aerodynamic forces, which of course is fluid mechanics on relatively rigid sails, and fluid mechanics forces on the hulls of these things, and also the aerofoils which are underneath the surface, which are adding stability and maybe lifting the hulls out of the water as they hydroplane. So it's actually an amazing design feat, I would say, to have these things going so fast. So that's that. What else do we have as we look through this? Let me pause that. Oh yeah, and so this is something that we'll use also. And you may have seen this before. Actually also, coincidentally, in the Bay Area, I think this looks like, to me, like SFO, San Francisco International Airport. And it's not an actual, it is footage of something, but it's not an actual event. It's a staged event to be able to, I guess, probably show in safety videos to encourage people not to drive their pickup trucks behind jet planes on the runway. And so you can find these things online. This might be the original one. There's also a Mythbusters one floating around. But the idea is that something that's powerful enough to be able to strap onto the wing of a 747 to be able to get, I don't know, 100 tons, a couple hundred tons of metal, which is slightly denser than air, off the surface and go upwards, actually must have a decent amount of force attached to it. And so, yeah, this is the runway at SFO. And the idea is just to have this, obviously, phantom pulled behind the airplane, and amazing power when you think about it. But not surprising when you think that those engines have to get such a heavy weight into the sky, and to be able to get it to trundle down a runway at, I suppose, getting up to a couple of 100 miles an hour, 100 and something miles an hour by the time it takes off in a very short period of time and a short length of runway, it's not surprising that they kick a bit of a punch. And of course, you know, those jet engines are the same jet engines which are used now with natural gas. You can't get a coal power station licensed these days, rightly or wrongly, because of the onerous burden of getting the emissions taken care of and siting these plants. And so the new solution to that, of course, is natural gas-powered plants that can spin up quickly, and they're basically spinning up gas turbines, which are just the same as jet engines, 747 engines, which are used for that. And so that's kind of, that puts us hopefully in the mood to be able to talk a little bit about fluid dynamics. And so that's our next quest, I guess, in this. We're going to talk a bit about fluid dynamics. So we've moved from one topic to another, from fluid statics to fluid dynamics. So it's a notable day in that regard. It might be worthwhile, there's a connection between them. It seems that they might not be so connected, but I think in the textbook, the part on fluid pressures at a point and fluid statics is actually joined to accelerating fluids. And we did that a little bit out of sequence in the book, but in our class, we touched on that on 4.1, looking at accelerating fluids. And it's quite relevant to this because it's really the entree to being able to say something about fluid dynamics, because we've already talked about fluid dynamics. You'll recall that we had a series of expressions which allowed us to, if we threw away all of the acceleration terms, that they came out to be very simple expressions. And those were that as you go horizontally, the pressure doesn't change. If you go vertically, the pressure does change. If you choose your coordinate system as z upwards, then this is the relation. Whoops, I didn't mean to do that. Then this is the relationship which defines that. This is always true, but if unit weight changes with pressure and therefore with elevation, the weight of material above it, then we can't just do this simple change so that pressure is equal to unit weight times height plus P0. This is only for an incompressible fluid. If unit weight is a function of pressure, then we have to make allowances for that. And the final portion of that was that we looked at the case where these are no longer zero. That's what we did last time. And we saw a couple of things which are relevant today. The first is that we could look, for instance, at the free surface of fluid within a tank. And if we look at that, I think it was dy in our particular case, but it doesn't matter. This is for an acceleration in the x direction. If we apply it, then we'd expect that this free surface rearranges itself. And it does it as a consequence of the fact that now the fluid is no longer static, although we said the fluid is sitting in a bucket and we're moving it, so it's not circulating. Has to circulate slightly, right, to be able to get into this configuration from being horizontally before. So it has to readjust itself. But it's not circulating as you would think in terms of streamlines flowing around the place. So that is us looking at linear acceleration. So you can think about that as being going along, dropping a leaf in a river, watching where that leaf goes. That's basically a streak line or a streamline, which is flowing downstream. And any molecule of water which starts upstream ends up at that location downstream, and it's flowing a relatively straight path. It could be a constant velocity, or it could be accelerating in that direction. So what we'll do is we'll look at z as our one direction, our directional coordinate, and we'll use this static description of fluid pressures to be able to pull out of our Bernoulli's equation, which many of you will have seen before. The second thing that we looked at was rotational accelerations. And so we illustrated this with this idea of, putting water in a bag and flinging it around your head and thinking about exactly what that would do to the fluid pressures that would result. And really what it would do is it says that something about the changes in pressure with radius, which is if you think about this spinning bucket. Now we talked about this. And it's turning around some center line, is that the gradient of this surface also, we can talk about P dP dr in this particular case, because we know that on this all lines which are parallel to the surface have equal increases in pressure as we go down. So you can think about this as being the gradient of this surface in some respect. And we know that the fluid gets thrown out to the outside of this curve. And so what we'd like to do is now take this, instead of being fluids inside containers which are either spinning or being translated laterally, and which seems a bit esoteric, is to be able to move it into something which is a bit more useful to us and to use it to apply to moving fluids. And so fluids moving in rivers, fluids moving around half-ton or three-quarter-ton trucks as you blow a jet from a jet engine on them, and using that in some useful way to be able to say something about what's going on. So that's our task today. So probably what we'll do today is we'll talk about defining behaviors along streamlines. I'll give you the punchline. You've probably seen it before. I think you saw it on the first day that we met for class. And without description, going back to our ideas of dimensional homogeneity, this is in units of length. This has to be units of length, and this has to be units of length. So if you haven't seen it before, don't worry. We'll talk about it. But ultimately, when we look at behavior along streamlines, we'll end up with the Bernoulli equation. So you'll all have seen this before. And you'll be sick of it by the time we get done with it, obviously. So if you haven't seen it. All right? So that's where we are. So you can go back to it. So we won't worry about the equation sheet. So let's just talk a little bit about ground rules for this, what we're trying to do. So we will look at flowing fluids. The requirement for the Bernoulli equation is that the principal one is that it is inviscid. And inviscid just means that the viscosity is 0. It's not true. Air has viscosity. Water certainly has viscosity. Relatively low viscosities, certainly in the case of air. But it turns out that actually Bernoulli works reasonably well even on fluids which have viscosity. It just has to be that you're solving a problem where the viscosity isn't kind of the central feature of your analysis. So if you're pumping stuff out of a gas well or an oil well, or a water well for that matter, or pumping fluids in your house, the essence of that problem is maybe dimensioning a pump to be able to flow it. If the only forces that are acting in your system, if viscosity is not acting in your system, which is a very large part of the fluid losses in these small pipe systems, as pipes get smaller, viscous forces get larger as you try and pump the same volume, then if you're trying to use an inviscid approach, you won't get the right answer. You'll get one that doesn't really represent the real problem you're trying to solve. So Bernoulli is good for some of our cases, and so in weeks 4 and 5, we'll use it exclusively. But if we're trying to solve pumping type problems, flow-in pipes, drag on external objects, you saw that SpaceX and Boeing, I think, got the contract for the new transport to orbit, to put astronauts up to the space station, etc. Well, that's a big fluid mechanics problem as well. You pump up the rocket, it would keep on going forever if there wasn't any drag on the atmosphere. So the essence of that problem is drag on the atmosphere. Drag is due to both pressure effects, which we accommodate in the Bernoulli equation, but also viscosity effects, which we don't. And so you'd miss the calculation if you're trying to do that. It would be the unfortunate NASA error where they designed something in meters and implemented it in feet, and surprisingly it didn't work. Can't remember, it was some satellite a number of years ago. Unfortunate situation. Okay, so we said when we started out on this that we use F equals ma. If you remember when we talked about fluid statics and accelerations, This is exactly the approach that we used. We used F equals ma, and so we'll use that again today. And the other constraints on using Bernoulli's equation are that the fluid should be incompressible. So that suggests that air is compressible, so you should be able to use it. Well, it turns out that it actually works okay. You can use it on air. You can use it on air at relatively low velocities. Once you get above the speed of sound, you get big compressions in airs, and you can't use it around a Mach number of 1. But otherwise, we can get around quite well. It should be straight flows which aren't in vortices, which is what irrotational is just a fancy word for. So it's without vortices. It should be steady. And so if you drop your leaf in the stream, the leaf obviously is moving, and therefore you'd think that was not steady. Steady means that if you look at the point where you drop that leaf at time now, and it's going at 1 meter a second due east, and you look 10 minutes from now, and it's still going 1 second due east, that hasn't changed, and therefore it's steady. It could be that the point downstream is going at 2 meters a second to the north, and in 10 minutes it's still doing that. That would still be steady. So steady means that if you look at, for instance, flow across a weir, and it looks like this now, and you take a snapshot 10 minutes later, it looks exactly the same, that's steady. Doesn't mean that this packet of water that sits here hasn't moved somewhere downstream and ended up somewhere else, which it would have done. It means that if you take a picture again, there's another packet of water, and it's going at exactly the same characteristics. Same pressure, same velocity, same elevation as location at that point. And so that's what our issue is. So steady means that it doesn't change. And inviscid means that the viscosity is low, maybe. And we'll see exactly what that means. These equations apply equally well to flow in surface streams as in flow in reservoirs, for instance, groundwater reservoirs, where it's actually flowing within porous media. But in this case, the whole essence of the problem is that permeability, for those of you who know what permeability is, and for those of you who don't worry about it, permeability is the mechanism by which frictional forces drag against something to be able to generate heat, to lose energy. So in other words, the same idea about pulling this bag across the table. I provide energy to get it here. It doesn't immediately spring back. If I want to get it to its starting point, I have to spend twice the amount of energy to get it back. And so flow in porous media is the same thing. The permeability is the mechanism by which we have frictional losses in the system. Friction in a physical sense here, Amontum's law. Friction in the viscosity sense here is the essence of the problem. And so those are the issues that we're dealing with. So we said as we came into this that what we're going to do is we're going to talk about flow along streamlines. We talked about flow along streamlines. So we could imagine the case where we can define streamline. Streamline is just the trajectory that a single particle would take as we go from upstream to downstream. And there are two components that are important for us in thinking about that. Clearly we can flow along a streamline. Should be just by going along this direction. And that is how you think of your classical Bernoulli equation applying, as we've just written out. Pressure head, elevation head, and velocity head. So pressure head, elevation head, and velocity head, right, as you've seen before. And that's maybe typically how you think about this behavior. So it allows you to be able to write this equation at 2 points and be able to compare behaviors of those. But the other part of this is you could imagine also going perpendicular to a streamline in this direction. I won't draw it as Z, but I'll draw it as N. This is my N here for the normal to the streamline. And so you could also go from this point here to another streamline, and you'd also want to know exactly what are these magnitudes, how do these magnitudes vary, as instead of going downstream along a streamline, how do they vary as you go across the streamline? And so we can apply Bernoulli, if you like, in both of those methods to be able to figure out exactly what's going on. And we will do that. And so that kind of rolls into this lower figure that you have here. is that if we look at a frame of reference, which we have here, I'm trying to, let me just make it smaller, I guess, right? So I can do that, get them both on the same time. So if we look at a frame of reference, we can look at flowing from point 1 to point 2 along this. We can write Bernoulli's expression at each of these points, and then we can say something about it. We can also write things to be able to say what happens as we go from this point to this point. And you know, just as maybe a taster of what's to come, if you think about, say, a bed profile that looks like this, and you have water flowing down here that kind of hugs this bed profile, then what would you kind of expect as you go across this, right? So if you go from this point to this point. So this is a streamline along here. It's the path that a particle would flow as you go downstream. This is also streamline. This also happens to be the surface. What would you expect to happen as you go across from the point on the surface to this? Well, if you, for instance, drew pressure versus, let's call it N, because I did it as N before, what would you expect? Well, you're going around a curve, and you could think of that lower part of the bed as being something that constrains the fluid from going any further. So it's almost like the external boundary of the bucket that we're spinning around. So you could imagine that being flipped around, if you're on a tether, the tether would have to be pulling you in. If the tether wasn't there, then you'd end up exerting a big pressure on here. And so I think if you looked at pressure change with radius, it would end up looking like this. It would increase as you go out to this boundary. And likewise, when you do the opposite, and you are going around this boundary here in the opposite direction, you know what happens if you're not constrained, you're not against the wall of the bucket on the outer free surface, and so you'd expect as you go up on this free surface that pressures may decrease. They can't decrease below atmospheric, but they'd be at atmospheric here, and as you'd go down, you'd get the opposite effect. So if you label A and B, this would be A and B. And so it entirely fits with our views of exactly what happens when we're looking at individual systems just based on our kind of accelerating static systems. So that's what I'd like to do here. So there's a bunch of pages of derivations. I don't want to do that, but I want to take a much easier, I think a much easier path for you to get to where we want to be for this. So humor me. So this is what we're going to do. So I'll slow down so we actually write something. That's the plan. So again, it's an auspicious day because we're talking about a new topic. Dynamics. And so what are we going to do? All right. So what did we do before? You'll recall this. So we talked about accelerating fluids. Am I deluding myself, or is my handwriting getting better? Am I deluding myself? All right, so what did we do for accelerating fluids? You'll remember this little diagram that we had. It was our differential cube. And so what we're going to do is we are going to choose a streamline that goes between 2 points that happens to have this differential cube on it. Well, first of all, we had our coordinate system that looked like this. Right-handed, you remember? Always right-handed, always pointing upwards. So this was X, this was Y, this is Z. We knew that we could take F equals mass times acceleration. We know that there are forces in each of the X, Y, and Z directions and also accelerations. But if we're only looking at Z, then we have the force in the Z direction is equal to mass times acceleration in z only. And without retracing our steps, we had the pressure here plus a change in pressure. We had a pressure here just on its own. We had a unit weight we had a weight of this block which is equal to the unit weight of fluid, which is rho g times the volume. And the volume is just equal to dx dy dz. I guess we could draw that on as well. I'm just doing this by way of reminder. That's wrong, isn't it? That's right, but this is wrong. So you don't. This isn't so important. And what else did we have? Oh yeah, we had this other one important thing. It was that we had an acceleration in the z direction. And so those are the forces that we had that acted on our system. And all we did was we resolved them. And I won't make us do this again, but I'll just quote the result. And for the static system, it turned out that we had something like change in pressure with elevation, if we write it out. We had the density of the fluid times gravity. And we had the density times the acceleration in the z direction is equal to 0. So that was our standard result that we had before. And we've used it, right? We've used it for the case that we have. I'm going to get rid of this box in a second, so don't draw the box on. This is our static part. dp dz is equal to unit weight minus unit weight. If we have accelerations we have to accommodate, then we can also accommodate those as well. So that's something we've seen. We could resolve in the x and the y directions. We get another set of equations, but we don't need those. So what can we do with this? Well, this clearly represents a packet of fluid that's accelerating. So if I took this fluid and it was a ball, I could throw it at the wall and it would bounce back and it would change directions and therefore change velocity. And so we can use this to represent flow as it goes from point 1 to point 2 and write this equation at two different locations. What we can also do is we can write the acceleration as the change in velocity with time. But we can also much more conveniently write this as what is called a convective acceleration. So I'm just going to multiply this by 1 by choosing dz over dz. And if I do that, then what I can do now is I can do two things. I can group this together and I can group the other thing together. And so I'm just going to write this as, let me write it as not partials but full differentials, d vz dz multiplied by change in location with time. Right? And so by doing this, what is this expression here? It's just a velocity, right? Change in location. If I'm at z1, so this has elevation z1, this has elevation z2. If I change elevation in a given time, then there's the reciprocal of those, the division of those, is just equal to that. So in other words, this expression here is equal to the velocity multiplied by the change in velocity with time. I'm just going to drop the z because we don't need that. And we can actually write this, and you can show this for yourself, as equal to a half change with elevation of v squared. Right? So those are equivalent to each other. And so if we want to, we can now substitute this into this expression, which is our static expression. You can do the differentiation on this, so just differentiate with respect to v squared, if you like, and differentiate by parts, and you'll find out that you end up with this being exactly equivalent to each other. And so we can end up with something that, if we now rewrite this, we end up with change in pressure with location, minus change in density with gravity. And now this new term is density multiplied by a half change with location of the term velocity squared, all in brackets. Hello. And I guess we should also keep the fact that this is equal to 0. So what do I want to do with that? I guess what I want to do is let's multiply everything by dz. And so if we do that, then we multiply this by dz. We multiply this by dz. And we multiply this by dz. And so this becomes 1. This and this become 1. And so we have minus change in pressure minus rho g dz minus a half rho v squared, all in brackets. And that equals 0. And so that's one way in which we can write it. And we can also do something in terms of integrating it. And if we do that, we end up, and instead of integrating it between limits between pressure at point 1 and pressure at point 2. So in other words, we would do it between these points here. So at this point here, there'd be an elevation z1, there'd be a pressure z1, and there'd be a velocity v1. And at this point here, there'd be a pressure of elevation z2, a pressure 2, and a velocity v2. So at each of these locations. So in other words, the dependent components of this. And so we could insert those as limits, or we could just do the integration with a constant at the other side. So let's do it the second way with a constant. So if we do that, then what do we end up with? We end up with minus p minus rho gz minus a half rho v squared equals constant. And that's Bernoulli's equation. It's in units of pressure. Everything should be units of pressure. This is a rho density. And the way I like to think about it is in terms of a length. So let's just divide through by density times gravity, unit weight, density times gravity, and density times gravity. And so we end up with the final expression we want. So this is exactly what we had before. They're all negative, so let's just make them positive. And so this is P over unit weight plus elevation plus V squared over 2g, velocity head. So we lose this, right? And because that is equal to constant, we could write it as equal to constant, which is above. Or we could also go back and realize that we could write it at 2 points. And since it's the constant value here and a constant value here, then we could also just substitute 2 values. So this is true if it's pressure at point 1, elevation at point 1, and velocity at point 1. This would also be equal to, just by writing the equation at P2 over unit weight plus elevation 2 plus velocity squared at 0.2 over 2g. That's it. So we've taken our static equation for fluid in a tank. We've realized that we can look at just the vertical component because that's the one which has the important part of unit weight in it. And so that's what gives us this term here, I guess. What is it? Yeah. Second term. This term here comes from the unit weight. So this term here comes from unit weight. And we've just manipulated that expression in some way to be able to come up with Bernoulli's equation. It has all the essential components of Bernoulli's equation because Bernoulli's equation is really just equating a force balance, saying that the total change in momentum And forces acting on something at this point is the same as this, because it balances through Newton's second law. And so if we have that, then we can do something useful with it to be able to do it. So that's it. So that's exactly where Bernoulli's law comes from. So that's the full way of doing it. There's also a way that we showed earlier that we can define it in terms of differential components, but that allows us to be able to solve some useful problems. So shall we solve a useful problem? So, I mean, how do we use that? I mean, basically this says that if you have flow, let's solve something that we've already looked at this morning. Let's see how my drawing is. Tell me what I'm drawing. There you go. Exactly. Fantastic. Ah. He's holding a shield. That's just Scottish shields since Cross of St Andrew, since they're looking for devolution. Okay, so how much does the truck have to endure to be able, before it gets blown away? Probably better with a truck. Doesn't matter. Since we talked about a truck already, what does a truck look like? Good enough. Not really a half-ton truck, something else, I guess. So we can apply that to look at solving a problem. And so the idea is to be able to look at a truck. We could look at the truck being just a flat face that it comes up against. And we could write this expression between points 1 and points 2. Nothing more than that. So we can use this expression to exactly do that. And so what do we want to, what don't we know in the system that we'd like to know? I guess we'd like to know what the force is that gets applied on this truck as a function of the saltation, stopping this velocity. So the mechanism is, I suppose, you feel it when you stand into the wind. You get the wind on your chest. The wind was going at some velocity here. Now it's going at 0 velocity because it hits your chest. And it transfers momentum to you, exactly the same as me throwing a ball at the wall. When the ball hits the wall, it transfers its momentum to the wall and then gets transferred back to the opposite direction to the ball to bounce back off. So we should look at what these individual terms are that define this behavior. So what is the pressure at point 1? What is the elevation at point 1? And what is the velocity at point 1? And likewise, the conditions at this other location. So, well, we could do something with the pressure in here. I guess we could call this point 0. It's going to be pretty high pressure in there, right? It's combustion. It's not isothermal. It doesn't really satisfy our conditions for using Bernoulli's equation. We saw that isothermal was one of them. There's a chemical reaction going on here because you're burning fuel and expanding it. And so we can't really use Bernoulli at this point, but we can at this point. So what's the pressure at this point? Well, all around it, it has atmospheric pressure. If you put a little tube in here that wasn't kinked over at the bottom, it would basically measure 0 pressure at all. It would measure atmospheric pressure. And so maybe take it on trust, but it should be atmospheric pressure because certainly there's pressure acting against this stream, and we said that pressure at a point has to be the same in every direction. And so it infers that if the pressure acting normal to this stream is 0, then it has to be also 0 pressure along the direction of the stream. So this is somewhere outside the engine. Clearly that's not true inside. The elevation, well, we choose our own datum. And so we can put that to 0. Velocity we don't know. We can guess. What's the pressure at this point? Well, we don't know that. That's what we want to find out. Because force is going to be equal to pressure times the area, for instance. We know the elevation is 0, and we know the velocity. At this point here, it's moving pretty fast. Actually, it's moving here. At this point here, it would be going at the velocity 1. But at this point here, where it hits this and then has to divert around this structure, remember, velocity is 2 things. It's its speed and also its direction. What's going in this direction? I'm guessing, what's the jet engine? In the air, a jet engine is probably making a plane go at 400 miles an hour, 500 miles an hour. I think that's about 200 meters a second. If the conversion's right, you can check. So away from the wall, it's going at 200 meters a second. When it's doing this, it's doing 200 meters a second in this direction, maybe, because it's just changed direction, but its velocity has changed. It's no longer going in the straight line. And so the velocity in the direction of the streamline is actually 0. And so we can use that. And so if we look at each of these expressions on the side, so velocity at 2 is 0, elevation here is 0. So we're going to lose, I guess I've done this backwards. This is 2 on this side. This is going to be 0. This is 0 on both sides. This is what they do in the book to do that, right? And the pressure at point 1 is 0 as well. And so we just have an expression, if I write it around this way, which is V1 squared over 2G is equal to P over unit weight, P1. This is what we want to know, and so we can just rewrite that as, I'll write this as rho G, right? V1 squared over 2G, lose this, is equal to pressure. We multiply pressure by area to get force. And this is what we want. So how big is the force that we have to sustain by basically killing off this, the momentum of this stream of air? So let's do the calculation. So, you know, I like rounding numbers off. So, truck. 3 meters is 10 feet. 10 feet. 3 meters by 3 meters is 10 square meters, right? So let's put some numbers on this. So this is our truck. I'm guessing this is 10 feet, which is 3 meters by 3 meters, which is about 10 meters squared. Something of that order. Density of air is about kilogram a meter cubed. Velocity, I think, someone can do the calculation. I think 400 miles an hour is right, and I think it's a conversion of a half to get miles per hour into meters per second. So I think velocity 1 is about 400 miles an hour, which I think is about 200 meters a second, which I'm going to actually make 100 meters a second, just because I can. And so what does this come out to be? The force is equal to area, density, velocity 1 squared over 2. It should be 10 to the 1 times 1. So what is this? Area is meters squared. Density is kilograms per meter cubed. Velocity is 100 meters squared. And I probably don't really care very much about 2, which is equal to, and velocity is meters per second. It's all squared. So let's figure out what the units for this. So we're going to want, can we write this? We want kilograms meters per second squared. So I guess we have, what do we have? We have 3 on the bottom, so we end up with, I guess we get rid of this, and this, and this, in which case we'd have meters kilogram per second squared. Actually, that's right. So exactly right. So 1 kilogram meter per second squared is equal to, right, by definition, 1 Newton. And so this works out to be 10, so 10 to the 4, 10 to the 5, 10 to the 5 newtons. And so this is the force required. So you can calculate the force applied to be able to do that. If you calculate that in terms of a kind of a weight that you have to overcome. What is that in terms of weight? So 10 to the 5 newtons equals 100 times is 10 times 10 kilonewtons, right? So 10 to the 5 newtons is 10 to the 1 times 10 to the 1 is 10 to the 2 times kilonewtons is 10 to the 5. And the only reason I do this is because 10 kilonewtons is the weight of 1 meter cubed of water, just for reference. And so I guess this is 10 meters cubed of water, 10 cubic meters of water. Cube root of 10 is about, so it's a tank of water that's about 2 by 2 by 2 meters. So 6 feet by 6 feet by 6 feet, basically. And so when the force becomes that order of magnitude, it would be able to, so I'm trying to think exactly, so how is that relevant? Well, it's relevant because if you look at the force that you apply due to this is our force at point 2, I guess, right? This is our force at point 2. Then the force that you could imagine resisting this, friction is about 0.5. So in other words, in this particular case, to move this, you'd have to apply a force which is equal to the frictional coefficient, not viscosity, times weight. If you remember this from your statics courses, friction coefficients are typically of the order of half. So the force you have to apply is about half the weight of something you're going to move if you want to be able to move it in some space. So since the force that's applied is this, then I guess this suggests that the weight of the truck is roughly twice this. Sounds about right. I don't know exactly. A truck probably runs a ton. A car runs a ton. So you can do the calculation to make sure that it makes sense. So, you know, what's the weight of us? You know, we're basically fluid, right? So that's why we float in the swimming pool, is because we're pretty close. You can use it from your understanding of buoyancy. We're neutrally buoyant in some respects. And so if you cram enough people into the Volkswagen and you fill it up, and it's 6 feet by 6 feet by 6 feet, that's basically of the order of magnitude of the force which is being applied to this to actually move it. So it seems to work out that it makes some kind of sense. Okay. So that's, I'm not sure there's much else I wanted to talk about today. So we've avoided, happily, a bunch of stuff. You can look through this if you want some other kind of a more conversational approach to what we're doing to understand it. It's important that we understand it. So really what we've done today is we've taken our previous expressions and shown that for static fluids, accelerating static fluids, Bernoulli's equation is just a consequence of those, because we're really only solving the one thing you need to know in this course, F equals ma. And we've used that to be able to make this balance between these three components that describe behavior. The potential energy something has, the elevation where it is, Z in other words, the pressure, force it applies on something, P over unit weight, and the momentum it has, V squared over 2G, which we might want to destroy. And if we destroy it by hitting it into a truck, then it produces a force as a consequence of that, which is really what F equals ma. There's a force that happens when a mass hits something and you destroy its acceleration. Changing acceleration is a rate of change of velocity, which is, of course, a change in momentum. And so you can think about the magnitude of those different components if you think about these three different points on a streamline. So a streamline would go up through here, and you change the case where something has a lot of potential energy, one where someone has a lot of kinetic energy, and one where it has a lot of pressure energy. And these are traded for each other as you go from one location to another. So the final, the punchline is, if you're able to say something about behavior at one point on a streamline and draw a streamline through a second point, so long as you only have one unknown out of the 6 components that describe that behavior, 3 upstream, elevation head, pressure head, and velocity head, and also the same downstream. If you know everything except for one variable, you can solve for that one variable. And that's basically what we did for this example with the truck. Thank you very much.